Hello, hi. I think this is probably the last talk. So, second last. Okay, there's one more. My name is Yuan Yu. I'm from Microsoft Research, and thank you for inviting me here, and also thank you for staying for a long 2 days of conference. So my talk is about Dryad and DryadLINQ. So the goal here is to make distributed data parallel computing easy, and it's accessible to every programmers and every developers. And this is something we have been working on for 4 years. And so there's a bunch of people working on it, and this is all my collaborators. And so what is Dryad and DryadLINQ? So here is a very high-level view of Dryad and DryadLINQ. So the developers write and debug their programs using Visual Studio and .NET on a single computer. And running the application, running the programs on the cluster is completely automated by the system. So DryadLINQ generates a distributed execution plan and shape the plan and also the corresponding code to the cluster. And the Dryad lives in the cluster, takes care of the execution, providing things like the fault tolerance and the scheduling. So the first question, I'll do it preemptively again, too, and following the last speaker. So the question is about availability of this thing. So the Dryad and DryadLINQ is actually available on the Windows HPC cluster, which is as a free download. You can download it from this place. And so we are releasing DryadLINQ in source code and Dryad in binary. The only reason we release Dryad in binary is because there's some dependency of Dryad on Microsoft internal stack. And we are trying to, it's our plan to remove the dependency and eventually get Dryad also released in source. So, and some people told me they are not very happy with the license associated with this release. And don't give up, and drop me a line, so we'll try to accommodate. So my talk is, so here's a brief outline of my talk. The first thing I'm going to talk about is the programming model, and I'll try to do a live demo, which is, let's see how it goes. And then I'll give you a very brief overview of Dryad and DryadLINQ, but this is very easy. I'm going to do it very fast because there are so many previous talks about PIG and about cascading. They all set up the stage for my talk. My talk is actually fairly easy. So, and then I'll talk a little bit about the applications and a little bit of something. I'll give a summary. So the programming model. So the vision is to use the cluster as if it is a single computer. So this is our vision. So that means we want to provide a sequential single machine program abstraction. And the same program should run on a single core, multi-core, or the cluster without any modification. And also we want to use familiar programming language. So this is just, we're talking about programming, so we should use a real programming language. And Java and C# are proven to be very, very good language. We should just use them, not reinventing any new programming languages. And also, we want to use the familiar development environment. So in our case, so we take a dependency on Visual Studio and .NET. So we want the developers to use all the .NET libraries and to use the Visual Studios as if they are writing their application for a single computer. So the foundation of this whole thing is something called LINQ. So I don't know, how many of you have heard of LINQ? Great. So LINQ is, I think, is probably the most innovative stuff coming out of coming out of C# for the past 2 or 3 years. So it's really, really nice, and so it's very nice. So it's available in .NET 3.5, and also it's available in the Visual Studio 208. What LINQ does is to define a set of operators to manipulate data sets in .NET. It supports the traditional relational operators, such as select and join, group by, and aggregate. What is unique about it is deeply integrated into a .NET programming language. The programs can invoke those operators, and operators can also invoke arbitrary .NET functions. So it's basically a clever way to integrate the declarative and functional programming into a seemingly imperative programming language. And also the data model is also very, very simple. It's just strongly typed .NET objects. We're not introducing anything like tuples and tuples and any kind of a new concept or new data set, new data models. And the model is just .NET objects. It's your Java class or Java objects. And it's very expressive, as we know. You can have graph, you can express graph, you can express linked list, you can express anything you want. And for DryadLINQ, the data model is just a straightforward extension of the LINQ model. And we add a new data type called partition table. The partition table implements exactly the same abstraction of the .NET collection, but the objects are partitioned and stored and distributed over multiple machines. But collectively, they provide the same high-level abstraction. And the partition tables exposes metadata information. And so, for instance, the type of the objects, how the thing is partitioned, whether it's hash partition or range partitioned, what are the range keys, and also what is the compression scheme, and even the serialization code is as part of the metadata of the table. And those things are used to give us, for us to generate better execution plan, and also is used for verify to verify the legality of the do some validation on the table. So now let's just I mean the most interesting thing is to see how it actually works. So let me try to do a demo here. So suppose I have a user web server log, and its partition is stored in a partition table. So I have a partition table, and that contains the web server log. The web server log essentially is unstructured data, and each line in the log is a log entry. So, and how do I write a program? So I just write a program just like what I write a .NET program. Write line the first thing I'm going to do is count the number of lines in the log. That's it. And now run this program. Oops. Okay, there's some compilation error, and also there's a okay, let's compile it first and run it. And when we run the program, and at some point during the execution of the program, DryadLINQ takes over and send a query to the cluster. And so this is actually, the whole program is actually running on a cluster in Mountain View. And what it does is from this execution graph, we have 5 partitions. What it does is to do a count on each partition and do an aggregate to count the total and to sum all the partial counts together. Okay, so this is a very simple program. Let's make it a little bit more complicated. I don't like. So now I want to say, well, I write a query. So I can write in SQL, in a SQL syntax, or in some other, in a non-SQL syntax. Let's first start with a single SQL syntax. X in Q where x dot line dot contains so the logs here, sorry. It's trying to tell me all the stupid errors I'm going to make. So say, for instance, I want to find something about, I'm only interested in the logs, the log entries for one particular person. And I'll say Levin, which happened to be a colleague of mine. And I'll say select of X. So this basically it says, OK, I'll do a filter. And now I'm only interested in the lines containing Levin. So I say for each var of X in Q, I'll do a console write line of X. So this is my second program. If I run it, oops. If I run it, it goes out and doing the execution again on the cluster. And this time, because of just a simple filter, and we filter it and on each partition, and then we generate another partition table that contains 5 partitions. And so because of doing a console write line, so this is what printed out.
How much data is in that cluster?
This one is a very small data. It's just for the demo. OK, but because we are not NoSQL conference, so I'm going to not to use a SQL syntax anymore. So frankly speaking, I hate the SQL syntax. I really like to write this way. And X, but this is a little bit of something which is a lambda expression. So I'm going to now write X dot line that contains of 11. So that's my program. That's the same program, but I mean, let's make it a little bit more complicated. But now so far, it's still a line, right? So it's still unstructured. So now I want to convert it into an object. So what I do is I do a select and take a line. But now I want to say new. I want to create an object. So here I define a very tiny class here. That's called log entry. So it's just your ordinary Java and C# class. And it contains a few fields. And you have a constructor. So the constructor, the first line of the constructor is to break a line into small pieces. And then so we get the user field and the IP field and the page field. So, and then what we do is here we say log entry of X. So now this is my program, but if you try to compile it, it may complain because of it's not complaining, but this is not going to be very useful because of I say print this object. There's no toString method, and so I need to do something here. I'll probably say the user first. I'll say the X dot, maybe IP. I'll say X dot, what else I have? Page. OK, so this is my program. I'll compile it and run it. OK, so the program is, the execution is shipped there, and also it's being executed. But this time, and because of the filter and also the transformation can be pipelined together, so it creates a super vertex that is executing the where and select as a pipeline. So obviously, and now we try to make it even more complicated. So suppose I want to figure out what are the most frequently visited page by this person. So, and obviously what I need to do a group by. I group by on the page, right? So I group by on the page, and after grouping it, I need to do I need to count how many the size of the group. That's give me the count of how many times he visits that page. So I do a select again, and this time it's going to be, so there's another little class I created called user page count, right? So I'll put 11 here, and so x dot key. So that's the key. So that's if you think about the MapReduce, that's the key. And dot x dot count. That's the size of the group. Cool. So that's a program. And but here, so because of I do another transformation, is this is a different kind of object. So which is just another object I defined here. That's a user page count. And now what we have is we don't have the IP anymore, and I just put a count here. So that's a program. And if we run it, so this is if you are familiar with MapReduce, this is exactly something like a MapReduce. Okay, so the graph looks like just what MapReduce is. And by the way, one thing I haven't told you is, because of that's the same program, as I said before, the same program can be executed on a single machine and multi-core and on the cluster. So all I need to do is, for instance, to say, I'm going to run this locally. I set a flag to run it locally, and I can set a breakpoint here, and I can step through it. Oh yeah, so that's too much a step here, but anyway, but you can step through it, and for instance, if you made a programming error, like instead of field 8, you say field 80. And if you run it locally in the debugging mode, you hit this breakpoint, and if you keep running, it tells you there's some exceptions thrown, and you mouse through it, and you can get a field. And you see, oh, yeah, this is all the field you have. And so you have only 14 fields, and you are referencing with index 80. So this is basically how this whole thing is integrated into as a programming language. Okay, now let's just modify. Okay, let's just stop this debugging and get rid of this bug, and then go back to our little program. But remember, I want to say the most frequently visited page, I need to do a sort. So I do an order by here, and I'm going to order it by the count. Okay? So now I run this program again. And again, so the computation is shifted to the cluster, hopefully. Let's see whether it's a, oh, no. Right, sorry. I need to make this thing not local. So now I'm running it non-locally, so that means it's shipping the whole thing to the cluster. So this is actually the execution graph of the sorting. So what happened here is so this is actually the start of the sort. So we first sample the data to find the range keys in order for the distributed sorting. And so this guy computes the range keys and distributes it back into all the partitions. And the partition basically, and then do a range partition based on the range keys, and then do a sort on each partition. So this is how the global sorting is implemented in DryadLINQ.
What if one of the components fails?
Oh, the component that fails, the Dryad is taking care of the re-execution of the vertices. And so that's something I'm going to talk about a little bit, which is, the idea is very similar to MapReduce idea, basically re-execution as the fault tolerance. So to just try to conclude my thing, and so eventually I want to do let's do a take 10, right? So I don't want to see all of them, and I'll do a take 10. So the interesting thing here is this time, we don't have to do a global sort. So what we do is we do a local sort on each partition, and we do a take 10 on each partition, and then we do another take 10. So this is pretty much the how you program in DryadLINQ. So this is the system. Now I'm going back to the talk and to tell you a little bit more about the system. So basically what we are trying to do here is this is just programming. We want to use the same programming languages, and people have been working on programming languages for decades, and inventing a new one, it doesn't make a lot of sense. And so we want to use the same development tools. We want to use the same libraries. So to give you a little bit more complicated programs you can write. So this is basically a well-known k-means clustering algorithm. And what you do is you define, everyone knows k-means, right? Okay. So basically you are trying to cluster points, a collection of points in the n-dimensional space, and based on L2 norm or something like that. So, and you define your vector class. So your vector class is just your vector class. You define in your first year programming class. So, and you define vector, and also is an array of doubles, and you define the addition, vector subtraction, and you define the L2 norm. That's it. And then you define something called nearest center. So you given a point and given a bunch of centers, I want to see the nearest center to this point. So this is written like this. And you probably don't want to understand it, but this is the code. And then what you do is it's an iterative program, and you take one step. The one step is if you look at it, it's very similar to a MapReduce. You do a group by, means you try to group each point to the nearest center, and then you recompute the center, the collection of centers, by doing an aggregation of that kind of thing. So this is the vector plus vector addition, and this is the count of the group. And the program is basically you say, okay, so I have a partition table. That's a sequence of vectors, and I'll choose I'll choose the first 100 points as a candidate for the center, and then I'll do an iteration on it. Yeah, and then after the iteration, I'll just write the center back to a file, to a partition table. So that's your program. And also, the very interesting thing is, remember there's something called associative So the declaring that function is associative. That enables a lot of interesting optimizations here. And especially, when people read the MapReduce paper, people know there's a combiner optimization. That is crucial to get good performance. But in this world, you don't have to specify a combiner. You specify a property about your functions, your libraries. And so the system is automatically going to figure out, this thing can be decomposed into combiners and some other things, and yeah, everything works. So this is how we do this. And this is how you write PageRank in DryadLINQ. And this is actually the entire program. So, and you start to define something called page. That's your page. A page is a unique ID and a bunch of links. And it's an array of links. And then you define your rank. The rank is the page ID and also some score, which is a double. And then you define the first iteration of PageRank. The iteration of PageRank essentially, I'm not going to go into any details about this thing, but it is a join and a MapReduce. Okay, it's a composition of a join and a MapReduce. And then what you do is you just like the previous one, you write this iteration here. That takes a page, and starting with a page, I'll initialize what the ranks are, and then I'll just iterate. And then finally write the ranks back into the stable storage. So this is actually the execution graph generated by DryadLINQ. So this is multiple iterations. I mean, this plan is actually, there's a lot of interesting optimizations in the plan. I'm not going to talk about it, but it will be very interesting to see whether you can do the same thing in MapReduce. But I've been trying to think about a way to do it in MapReduce, but it's just very, very hard. So what it does is actually the first, for each iteration, it does a join, and it's pipelined with the map, and does some kind of shuffle, and we do some and then we apply the reducer. And the interesting thing here is, and the system can figure out the thing produced by reducer is partitioned the same way as the page. Okay, so therefore, we can, for the second iteration, there's no shuffling at all. What we do is we basically do a pairwise join again. And the pipeline of the join and also the mapper is actually turned out to be quite interesting and important because of the join, typically there is a blow up. And you don't want to have that blow up. You should try to get it to the mapper as quickly as possible in memory. So therefore, you get the reduction, data reduction. And also, what is MapReduce in DryadLINQ? So this is actually the function you define, the MapReduce you define in DryadLINQ. It's a select many and a group by and a select many as a function. And you can use this function arbitrarily in your program, and it can be composed with some other queries and generating some even very fancy commutation. So enough about the programming model. So let's go to the Dryad and DryadLINQ. I'm not going to talk, there's a lot of techniques used, for instance, in Dryad. It's very similar to MapReduce. For instance, the fault tolerance is achieved by doing re-execution. But I'll just go through a few slides. So first, so this is the software stack we're building. At the bottom is a Windows server. No, they are not Linux box. So, and we have a layer of cluster service. So that basically is that, for instance, name server to understand the machines, and also the topology of the cluster, and also there's some kind of a process daemon that allows you to understand what, to start processes, running the mappers and reducers, and communicating with the job manager. And also, we support all kinds of storage. And also, there is a generic data provider that allows you to plug in arbitrary data providers, data source. And so, yeah, so Dryad is sitting on top of this. And the DryadLINQ is sitting on top of Dryad. And so then we have the applications. So Dryad, okay, I'll just have one slide on Dryad. Dryad lives in the cluster. Okay, a new job arrives at the scheduler, and the scheduler controls the degree of concurrency, how many concurrent jobs running in the cluster. And it starts a job by forking a job manager. The job manager manages the data flow graph, the acyclic data flow graph, and talks to the vertices, which is the running vertices, considering there are mappers and reducers, and and providing fault tolerance. If some guy is running very slow, just kill it and run it someplace else. And so this is pretty much what Dryad is. But there's a paper on this, and you can read the paper with all the fine details about Dryad. So what is unique about Dryad is it provides a general flexible execution layer. So you can think about this is the assembly language for data center, for cluster. It provides a very, very general data flow graph as a computation model. And the data flow graph can be modified at runtime for runtime optimizations. We use this to do all kinds of runtime optimizations. And also, and it's very generic. So therefore, all the higher language layer supplies the graph, how the graph is constructed, and the vertex code, and even the serialization, and also some kind of hints for data locality. And so the job of Dryad is basically to schedule the processes on machines near the data to achieve data locality, and also is for fault tolerance, and also for fair scheduling of the concurrent jobs. That's it about Dryad. So DryadLINQ. So let's first introduce the LINQ framework. So LINQ framework is, even though we are not open source, but LINQ framework is extremely open and extensible. It's amazingly open and extensible. So it basically what LINQ framework LINQ is an interface. It defines an interface, and also provides a way for you to write arbitrary execution providers for this interface. So there are many, many execution providers written for this interface. And for instance, there's an XML provider, there's a SQL provider, there's a PLINQ provider that's for parallel multi-core machines. And the DryadLINQ is sitting there as trying to do the execution on the cluster. So because of this, your program may not know where it is going to be executed. So you write your program as just generic LINQ programs. And that depends on where the data is, and then the computation is shipped to the various places. So this is the basic idea of LINQ. And this whole thing is open in the sense of anyone can define a LINQ provider. For instance, for DryadLINQ, we don't use any internal API. Everything is public. So here is just a very, very high-level view of the DryadLINQ system. So on the left, you have the program executing. And at some point, the execution is the execution of LINQ query is triggered. And so the query is shipped to DryadLINQ. And so the query expression is shipped to DryadLINQ. And DryadLINQ generates a query plan. And so you invoke Dryad. And Dryad takes the query plan, the vertex code, and where the table is actually inside the cluster, and it does the computation, and it generates the output table. The output table is, the abstraction of the output table is a collection, and it's a .NET collection, and it goes back here, and we can do arbitrary things with that collection. So there's a few things DryadLINQ does. The first thing is to generate a distributed execution plan. So this is very similar to what SQL does. There's it's a query optimization problem. It's a little bit more complicated than a query optimization problem because we're talking about a very general DAG. We're talking about, we introduce operators like you can fork the data. So in SQL, the output of an operator, you can only have one output of the operator, right? But here, so you can have multiple output of the operator, and so there's some complications there. So you do static optimization, also you do dynamic optimization. The dynamic optimization is basically we depends on the size of the data and depends on the sampling we do, and we generate the different kind of keys to partition the data. It's data dependent. And also we also take advantage of the topology of the cluster. For instance, if you want to do an aggregation, you might want to introduce multiple layers of aggregation. So you do a rack level aggregation, and you do machine level aggregation, you do a rack level aggregation, and also, and for instance, in the MapReduce paper, they talk about the aggregation they talk about is machine level aggregation. So, and also it provides a vertex runtime. So it has essentially a single machine implementation of LINQ, so which is part of the DryadLINQ. And also it breaks the query into pieces and has to generate the code running on the vertices. And also we do code generation to generate much more efficient data serialization code. We don't rely on the .NET serialization because of its a little bit the performance is not that good. So, and also it also generates a callback code, which is essentially the Dryad provides an interface that allows you to add some callback code to modify the graph. So this is the callback code. It's automatically generated by DryadLINQ. And all this stuff is generated and compiled into a DLL and shipped to the cluster automatically. And we are a friend of SQL, by the way. So for instance, we actually work, the system works with SQL. So this is how this is combined. So what happens is a query is, the DryadLINQ breaks a query into subqueries. And the subqueries are itself a LINQ query. And we can actually shape the subquery into SQL by taking advantage of the LINQ to SQL provider. So the LINQ to SQL provider is going to take the subquery and execute it on the SQL server. So this is a very interesting integration of interoperability or integration with some other providers. But we are using some other providers too. We're using PLINQ for parallelization on the single machine, and we're using, some people have some application. They write some custom LINQ providers, and so this is how it works. Okay, applications. So Dryad has been in production use for quite a few years. It is actually the execution engine for Bing Analytics. And it does all the heavy lifting for Bing. It runs on tens of thousands of machines, and also it runs on clusters with 3,000 machines. And it processes many petabytes of data every day. So, and also Dryad is the execution engine for DryadLINQ. So here are some examples of DryadLINQ applications. This is only a limited sample of the application. So for data mining, so people are analysis of service logs and analysis of Windows Watson data, and cluster monitoring and performance analysis. And for graph analysis, we do something like you do the page ranking, and you do some processing for shortest path, which is turned out to be is very useful to compute the driving directions for map. So, and also the image processing is the image indexing images, and decision tree training, and some other epitope computation, and simulation a lot of them are very either compute intensive or data intensive, and it was written for previously for some other platform, and because of the scalability and performance, they ported their stuff to this platform. And so I'm going to just mention a few of them. So the first thing is about network security. So it's a large-scale data mining. So this is, none of this work is done by me. So so I don't know much about them too. So this is actually the slides they created by those guys. So the problem is you have many log files, like Hotmail login file, user login file, the search logs, and Windows update logs. And what you want to do is you want to do some kind of correlated study, analysis of those logs, and trying to understand things like to identify the dynamic IP ranges, and to find botnets, and to find the search botnet traffic. So this is a very large quite a large project that contains multiple pieces. And so, for instance, the bar graph is an application that basically tries to construct a graph from the Hotmail user login data. And so the graph they constructed is something in the range of like 10 to the 8th nodes and 10 to the 11th edges. And the graph construction time is of about 1.5 hours on 240 machines. And then after the construction of the graph, they do some sort of a connected components analysis, which is it takes about 7 minutes. And so here is, for instance, the execution graph of the particular for the graph construction, and it's quite substantial. And the interesting thing here is it does all kinds of drawing and broadcast. So the second application is a decision tree training. So basically, you have some ground truths about some labeled images, and you want to generate a decision tree using something. So here are the parameters of the problem. So it's 1 million images, and for each image there's 10,000 pixels, and you have something like 2,000 features, and you're training a tree of 2 to the 21st level, 21 level. And you can think about it, now you can look at the complexity, it's quite complex. So here is, for instance, a sort of kind of a simplified execution. And I'm not going to say much about this execution. But it's just for one. This shows one level of the decision tree training. So it's going to be iterative, and after 21 iteration, you get to the end of the final tree. So for this application, it consists of 37 DryadLINQ jobs, and it's 12 hours of running time on 235 machines. And every day we have to recover from a few failures. So that's the fault tolerance is extremely important. And altogether, this thing is actually it's 35,000 lines of code. So, and some other folks in Windows, and they try to study what the data we collected. That's the Watson and Scream data. So, and somewhere in the middle, so this is Dryad and DryadLINQ. So it does the first line processing of the raw data into some structured thing and put it into the data marts. And also some people are trying to do some machine learning platform for health solution related stuff, to understand for cancer prevention and all that kind of things. And so this is the platform they built. It's funny thing is built on top of F#. This is our functional programming language. And so, and here, so they want the ability to do MPI kind of computation, and also they want to do, this DryadLINQ kind of computation. It's a very nice platform. So to summarize, so hopefully what I showed you is a single unified programming environment. And so there's a unified data model and programming language. And so because of this deep integration of language and also data parallel computation, and so you have the direct access to the IDE and also the libraries. And the Dryad DAG model is very expressive and powerful to express a lot of optimizations we want to do. And also, the system is open and extensible. And it's very easy to write a new data provider, not a data provider, a LINQ execution provider for your application domain. And we have a number of existing ones, and some of them are in product, and some of them are, people are writing all kinds of things. LINQ to Amazon, for instance, some people write this. And so the job of Dryad and DryadLINQ is to scale out all of them. And so here is a few Dryad and DryadLINQ related papers, and so they are. If you think this is actually interesting to you, and so you might want to read them. Okay, that's pretty much my talk. Yes.
I'd like to hear a little bit more about checkpointing, and in particular, I'm a little curious about how you do checkpointing, because you have these options about how you could actually execute these workflows. In the examples you showed us, you're running a program, right?
Yeah.
That then can be a distributed workflow and have some checkpointing and fault tolerance automatically in there.
Yeah.
For some of the bigger applications, you're probably not running that as a single app. So how do you find people use it?
Well, so typically what we run is for iterative application, we run 10 iterations, and then we checkpoint, right? So you write a double loop.
And those are separate?
It becomes a separate programs, right? So.
You still have a flow management system on top of that.
Yeah, okay, so, but even with a single large program, right? So because of most of the communication is by files, just like MapReduce, right? You can basically re-execute by rereading the files generated by the previous stage of the computation. And obviously, if the previous stage of the computation, the files is missing, and there is a recursive, it's a cascading effect, you have to just go back until someplace you can actually execute.
Hi, another question.
Yeah.
I've been talking to many people here, evangelizing about LINQ, so I'm one of those crazy people, and you're one of those crazy people that's not using a Mac and making presentations. You're very brave. So I was wondering about F#. The conferences I've been to, all the functional programming researchers think that Microsoft has done a great job with F# and integration with .NET. So is F# really a first-class citizen in the system that you've been talking about?
Our system is one layer below the language layer. Okay, so we support arbitrary languages as long as it's a .NET language.
So
okay.
The first-class citizenship of F# in .NET
yes, but as I show you in one of the examples, and so people have been people write F# programs and with Dryad and DryadLINQ. So I mean, yes, the answer is the first F# is going to be the first-class citizen as a programming language in .NET, and is, I believe, you correct me, I don't know. I mean, I think it's right. It's going to be in the next release. F# is going to be part of the Visual Studio, and also F# supports LINQ. So therefore, and so there's no question at all. So this whole thing runs. You can write F# program, and doing this commutation.
Thank you.
Thank you.